Hello everyone. Today we are continuing with the solutions lecture 6. Okay, already 5 lectures we have finished and now lecture 6 we are going with. Now in solutions what we have discussed so far is that solubility of substances in solvents, and also we discussed about what? Henry's law yesterday. So now here I count Henry's law. Whenever a solute, whenever a gas is combining with water, means solvent. Whenever a gaseous solute combines with the liquid solvent to form a compound. Okay, in this condition, this gas, ammonia gas, is more soluble in what? Water. More soluble in given solvent. And here also CO2 is ready to combine with the solvent water. Now as CO2 is ready to combine with water, CO2 is more soluble in water. So this point we have to understand. So this is about what now here, the combination of solute with the solvent to form compounds. Okay, ma. So just a moment. Hold on. Yeah. Yesterday we discussed about what now here this concept, and also we discussed about this one, hemoglobin. Hemoglobin, when it combines with oxygen, that means what? When oxygen combines with hemoglobin in the blood, so hemoglobin is present in blood here. So this oxygen, when combines with hemoglobin in the blood, the oxygen will be dissolved in blood. The oxygen dissolves in blood as oxygen gas combines with what? Hemoglobin, to produce what? Oxyhemoglobin. To produce what now here? Oxyhemoglobin. Okay, so this is what now here, the affinity of hemoglobin towards what? Oxygen. Okay, next. Applications of Henry's law. Applications meaning what? Uses. So uses of Henry's law. Applications of Henry's law. Okay. So now here, soft drink bottles are sealed at high pressure. First application, first use of Henry's law, what? Where we can apply Henry's law here? Soft drink bottles, cool drink bottles are sealed. The cool drink bottles are sealed at high pressure. At high pressure to increase what? The solubility of CO2 in the soft drinks. So in the soft drinks, what will be there? CO2 gas is dissolved in liquid water. Liquid water. Now water is acting as what now here? Solvent. So in the given liquid solvent, what is dissolved here? CO2 gas is dissolved here. So this CO2 gas acts as what now? Solute. Okay. So now here, any gas in liquid. Okay, when a gas is dissolved in liquid, if high pressure of gas is applied, if high pressure is applied on the gas, more solubility will be there. That's why to make CO2 dissolve more in water in the soft drinks, we apply what now? High pressure and seal the bottles. Okay, next one. At high altitude means at higher heights, means what? Higher altitudes means when you go up in the sky. Okay, when you go to higher altitudes, what happens now? Partial pressure of oxygen will be low in air. In the air, the partial pressure of oxygen is low. In the air, what will be the generally? There will be oxygen gas, there will be nitrogen and CO2. Now here, partial pressure of oxygen will become less. Partial pressure of oxygen becomes low at higher altitudes. When higher altitude is, the pressure becomes low. Generally, we know. When we go to the heights, what happens now? The pressure will be decreasing for the gas. So the partial pressure of oxygen becomes low. It leads to the low concentration of oxygen in our blood of the people living there. So the people living at the higher altitudes, in their blood, less oxygen concentration will be there. That means what? The solubility of oxygen will be less in their blood. The solubility of oxygen is less in the blood of the people who live at higher altitudes. Reason is what here? Why oxygen is less soluble in blood of the people there at higher altitudes? Because the partial pressure of oxygen will become less at higher altitudes. When partial pressure of gas is less, the solubility will be less. That's why the less soluble means less oxygen will be soluble in blood of the people living at the top of mountains. Next, low concentration of oxygen develops one condition called anoxia. One condition called what? Anoxia. Whenever oxygen concentration is less in the blood, okay, that condition is called what, ma? Anoxia. What is that? Anoxia. That is unable to think. and properly act. Unable to think properly and unable to act properly. So when any situation, dangerous situation comes, our body immediately reacts. Our body immediately reacts and acts wisely. So that ability will be lost. That is called what now? Anoxia condition. Okay. Next, another application is that when scuba divers, the people who will go to the deep into the oceans, the people who go to the deep into the oceans called what now? Scuba divers. So when the scuba divers go deep in the sea, when they go deep in the sea, solubility of atmospheric gases. Solubility of atmospheric gases means what will be gases here in atmosphere: nitrogen, oxygen, etc. So these gases, the solubility of these gases increases in the blood. Why? When you go deep in the sea, when you go to the depth of sea, what happens now? The pressure will be more. Pressure increases. When you go deep into the ocean, what happens? The pressure will be increasing, right? When pressure increases, okay, when partial pressure of oxygen increases, its solubility becomes more. When partial pressure of oxygen is more, its solubility in the blood will be more. So like that here, more oxygen will be dissolved in the blood of the people, and more nitrogen will be dissolved in the blood of the scuba divers. Okay, so it increases in the blood. Solubility of oxygen gas, nitrogen gas increases in the blood. Okay, ma. Next, when the scuba divers come up to the surface, when the scuba divers come again to the surface, what happens? There is a release of dissolved gases. Already some gases dissolved here. The nitrogen dissolved, oxygen dissolved in the blood will be released. Okay, there is a release of dissolved gases, and it leads to the formation of some bubbles of oxygen and nitrogen. Okay, some bubbles of nitrogen mainly. The bubbles of nitrogen will be formed in the blood vessels. Is that clear, ma? So when the divers come up to the surface, what happens there? There is release of dissolved gases. Why dissolved gases are coming out of the blood? Because the solubility becomes less now. When they come to surface from the depth, at the depth, what is there? High pressure is there. At the surface, low pressure is there. When the people come to the surface, the pressure becomes relatively lower. When they come from depth to surface, what happens now? The pressure becomes less. When pressure becomes less, what happens? The solubility of gas in the blood will become less. That's why the excess nitrogen dissolved in the blood will be coming out, will be released in the form of bubbles. Now these bubbles are formed in our blood capillaries. So in the blood capillaries of the scuba divers, what will be forming? The bubbles of nitrogen will form. The bubbles of nitrogen gas will be formed. And hence, there is a painful sensation. There is a painful sensation called bends, B-E-N-D-S. So bends is the condition where the nitrogen bubbles are formed when the scuba divers come to the surface and cause what? These bubbles cause what? Painful sensation. And this condition is known as bends. To avoid bends, to avoid this condition, the tanks of scuba divers, the oxygen tanks will be there. Na? The oxygen tanks of scuba divers are filled with 11.7% helium. Okay, not only pure oxygen and pure nitrogen, pure air will not be there. Along with oxygen, what will be there? 11.7% helium, 56.2% nitrogen, and 32.1% oxygen. Generally, in air, what will be there? In air, how much percentage of oxygen? Only 21% O2 will be there. Okay, now we are taking what now? 32%, 32% oxygen gas, 56.2% nitrogen gas, 11.7% helium gas. So when you take this mixture now, helium, nitrogen, oxygen mixture, when you take, the formation of nitrogen bubbles will become less. The bends condition can be avoided. Is that clear, ma? So this point is to be understood clearly. Once take the screenshot of this. Whenever you come across the new point, new word, immediately write down in the notebook or take screenshot immediately. Okay, ma'am. Now next one's here. Now gases, important notes. Important notes were first one, gases are less soluble in aqueous solutions. Gases are less soluble in aqueous solutions of electrolytes than in pure water. That means what now here? The gases are more soluble in what? Pure water, but less soluble in what? Solutions of electrolytes. Electrolytes means what? NaCl solution. Suppose NaCl will dissociate into Na plus and Cl minus in aqueous solution. So in aqueous solution, Na plus is available, Cl minus available. So in these aqueous solutions of electrolytes, the solubility of gases will be less. But in pure water, the solubility of gases will be more. It is called salting out effect. This effect is called what? Salting out effect. Whenever a salt like NaCl, whenever a salt like NaCl is present, what happens now here? This NaCl salt will not allow this gas to dissolve. But in pure water, salt is not there, na? In pure water, salt is not there. In this condition, what happens now here? The gases will be more soluble. Is that clear, ma? So that point keep in mind. Next, non-electrolytes such as sugar. Non-electrolytes such as what? Sugar, if present in a solution, also reduce the solubility of gases in water. That means what now here? Sugar is what? Non-electrolyte. What is the formula? C6, sorry, C12. Sugar means sucrose, na? C12H22O11. So in this, when sugar is dissolved in water, we get sugar water. Sugar solution we get. In this sugar solution, the gases will be less soluble. But in pure water, more gases will be dissolved here. Means gas will be dissolved. The solubility of gas in pure water is more, but the solubility of gas, the same gas in sugar solution will be less. Is that clear, ma? So in solution and pure water, in pure water and in the solution, where more gases will be dissolved, the solubility of gas will be more. The solubility of gas will be more in pure water than in any solution. That point we have to keep in mind. So just a moment, just hold on. Yeah, one moment. No? Yeah, once anybody is, tell me, ma, can you clearly understood what I said now? Did you understand clearly? Anybody open means unmute yourself and talk to me. What did we discuss so far now? What did we discuss so far? Anybody respond, talk to me. Henry's law we discussed now. In Henry's law applications we discussed, or we have discussed about the drawbacks, limitations. What we have discussed now? Anybody respond? Yeah, now see. So far you did not see the what is screen, na? So this is what we discussed here. So what is this now here? The applications of what here? Henry's law. Applications meaning what? The uses. The uses of Henry's law. What are the uses here? First thing, what we understood here, the CO2 in water will be there in cool drinks, in soft drinks. So in soft drinks, the CO2 will be dissolved at what pressure? High pressure. At high pressure, CO2 will be more soluble. Okay. Next, at higher altitudes, some people will be living. Some people will be living at the top of mountain. They are at higher altitudes. In that condition, the partial pressure of oxygen will be less in the air. That's why less oxygen will be dissolved in their blood. When less concentration of oxygen is there in the blood of the people there, that condition is called anoxia. If less concentration of oxygen in the blood is present, that condition is called anoxia. That people are unable to think properly and unable to act properly. That condition is anoxia. And the next thing is what? Scuba divers. The scuba divers will be going to, now it is surface of sea. It is surface. And when they go to the deep of the earth, the deep of the sea, means what? When they go deep in the sea, here high pressure will be there. In the deep in the sea, what will be there? High pressure will be there. So at the surface, what is there? Low pressure is there. So when the people go to the deep of the sea, what happens? The pressure will be more. At high pressure, more gases will be dissolved in the blood. In the blood of the people, in the divers blood, more what your gases will be dissolved. And when they come back to this surface again, when they come back to the surface of the sea, what happens? Already dissolved gases will come out in the form of bubbles. Okay, because here at surface, what is the low pressure is there? When they're coming from depth to surface, what happens now? High pressure to low pressure, they are coming. So at high pressure, more gas is dissolved. When they come to surface, that is low pressure, what happens now? That the excess dissolved gases, will be coming outside. Okay, they will be released, and the bubbles of nitrogen in the blood vessels will cause what painful sensation called BENDS, bends. To avoid the bends, what we use here, 11.7% of helium and 56.2% nitrogen and 32.1% oxygen. These gases will be taken in oxygen tank, and these tanks will be carried by the scuba divers. Okay, so this point we have to understand here. Generally in the air, what will be their percentage of air, percent of oxygen? 21% oxygen will be there in the air. But in the scuba divers tank, oxygen tank, how much percentage is there? 32% is there oxygen. And next, what we discussed here, so gases are less soluble in aqueous solutions. Gases are less soluble in aqueous solutions of any salt, any electrolyte. But gases will be more soluble in pure water. So in pure water, more soluble. In the pure water, gases are more soluble. But gases in aqueous solutions will be less soluble. And here, if you take sugar solution and water, pure water and sugar solution, in which case the gases will be more soluble. The gas is more soluble in pure water, but gas is less soluble in sugar solution. So this point you have to understand clearly. Okay, so it's about what now here, the concept of for this one. So now here, next concept is that the utility means usage of solubility curves. Solubility curves, utility. So yesterday we discussed now solubility versus temperature. Solubility versus temperature graphs. Some in case of some salts, the solubility will be increasing when temperature increases. In some other cases, solubility remains same as temperature increases. As temperature increases, solubility remains nearly same. It is, suppose you take KNO3. KNO3 solubility will increase when temperature increases. And NaCl. For NaCl, the solubility remains almost same when temperature increases. And in case of cerium sulfate, what happens now? It will be decreasing. Solubility will be decreasing. So cerium sulfate solubility will decrease when temperature increases. So this curves are called what now? Solubility curves. So the solubility curves, how they are used? The utility means what? Usage. The usage of solubility curves. First one's here. The solubility of a given salt. The solubility of a given salt at any temperature can be read directly from its solubility curve. By observing solubility curve graphs, we can directly say the solubility of the substance at any given temperature. By looking at solubility curve at a given temperature, what is solubility of that salt, we can say. That is first use. And the nature of curve gives an idea about what? The effect of temperature on change of solubility. Suppose if we take now solubility of exothermic solutions. So solubility of formation of exothermic solutions will be what now? Inversely proportional to temperature. Okay. So if the substance is showing what forming what exothermic solution, if a substance is forming exothermic solution like the CaO, like what? CaO in water. CaO in water will form what now? Exothermic solution. That means when you dissolve CaO in water, some heat energy will be released. That is exothermic dissolution. So solubility in case of exothermic dissolution or solution will be inversely proportional to temperature. That means when temperature increases, what happens? Solubility will decrease. And also, if you take endothermic dissolution means if we dissolve glucose in water will produce what now here? Glucose solution. This glucose solution is formed by absorption of heat energy. Okay, that's why the glucose solution will be cool to touch. When you touch the outer surface of glucose solution vessel container, we feel what? Cool to touch. Okay, it will be cool to touch because what now here? Endothermic dissolution. This type of dissolution is called what now here? Glucose in water dissolution is called endothermic, not exo. Endothermic dissolution. So in case of endothermic dissolution, okay, what happens now? The solubility is directly proportional to temperature now. Solubility and temperature both are what? Directly proportional. So in place of solubility, I'm taking S here. S means solubility, take here. So solubility of the substances which form endothermic solutions will be directly proportional to temperature. More the temperature, when you increase the temperature, more substance will be dissolved. Means solubility will increase with the temperature. But in case of exothermic dissolution, solubility is inversely proportional to temperature. Okay, a steep curve. Steep means sudden like this here, sudden increase like this. A steep curve indicates what? A rapid change in solubility. While a flat one indicates rather a slow change. Flat curve. If the curve is like this, flat, this indicates a slow increase in solubility like this. Okay, if it is like this, suddenly more increase in the solubility. If the steep is more solubility. If steep is less solubility when temperature increases. That point we have to understand. Okay, so it's about what now here? Applications of what? Solubility curves. Next. Now, the substances whose solubility decreases, substances whose solubility decreases with rise in temperature are what now? NaOH, Na2CO3, Na2SO4, and cerium sulfate. In all these cases, what is happening here? The solubility decreasing. The solubility is decreasing with what now? Rise in temperature. Rise means increase in temperature. Rise means what? Increase. So with increase in the temperature, what is happening now? Tell me. The solubility is decreasing. So how the solubility related here? Solubility is inversely proportional to. Solubility is inversely proportional to what now? Temperature. When temperature increases, solubility decreases in these compounds. Like what? NaOH, Na2CO3, Na2SO4, cerium sulfate. Next, substances whose solubility increases with rise in temperature are what? Examples? NaNO3, KNO3, KCl, ammonium chloride, all these here. So these all are what now here? In all these cases, solubility is directly proportional to temperature. Solubility is directly proportional to temperature means this type of dissolution of the compounds in water will be called endothermic dissolution. We say endothermic dissolution. Endothermic dissolution. This solution formed will be cool to touch. Endothermic dissolution it is. So in case of endothermic dissolution of the substances in solvent, the solubility is directly proportional to temperature. But here these substances will show what now? Exothermic dissolutions. So in these cases, what now here? This type of dissolution is what now? Exothermic dissolution. Exothermic dissolution. So in case of exothermic dissolution, the solution will be hot to touch. If you touch outer surface of the container of this solution formed, it will be hot to touch. That's why exothermic dissolution. Whenever you dissolve NaOH in water, okay, the solution will be hot to touch. That means exothermic dissolution has taken place. In case of exothermic dissolution, the solubility is inversely proportional to temperature. Okay, next, substances whose solubility fairly increases or sometimes no change with rise in temperature are what? NaCl and lithium sulfate. Sodium chloride and lithium sulfate, the solubilities will be very slightly changing. Okay, so fairly increases means for now here slightly increases, slightly, not fairly here, slightly. So slightly increases solubility slightly increases. Otherwise, there is no change at all. With what? Increasing with rise in temperature. When a rising temperature for NaCl, we understand now solubility versus temperature. The NaCl curve will be like this. NaCl curve. That means what now? Very slight increase in solubility when temperature increases. So this is what now here solubility curve of NaCl. Okay. So this point we have to understand here. And it's about what now here the solubility concept. Okay, and another important points what we have to understand is that on boiling, water loses what? Its taste. So the boiled water and the water before boiling, which will be losing its taste? The boiled water will be losing its taste. Tell me why? On boiling means what we are doing? We are increasing temperature now. We are increasing temperature. When you are increasing temperature, what happens? Solubility of gas will decrease, na? Solubility of gases in water. Solubility of gases in water will decrease. Whenever we increase temperature, what happens to solubility of the gas? Solubility of the gas will decrease. That means if you take some water, okay, when you are heating it, when you are boiling it, when you are increasing temperature of this water, what happens? Already dissolved gases will come outside because solubility will decrease. When gases are going outside, the water becomes what? Tasteless. The water becomes tasteless. Now see here, water contains soluble gases. Water contains some soluble gases which contribute to the taste of water. The water is having some taste because of what? Dissolved gases. But when you boil, what happens? The dissolved gases from the water will escape. Okay, like that. Next, on boiling, the temperature of the water increases, no? Thereby, the solubility of the dissolved gases decreases. Whenever temperature increases, solubility of the gases decreases. And the dissolved gases are hence expelled out. Expelled out means released out. They will be coming out of the water. They will escape from the water. If the above water is once again shaken with air, suppose you take the water in a vessel, open vessel, and shake it, then what happens? Some more amount of gas will again dissolve into the water. Okay, if the above water, pure water, is once again shaken with water or air, what happens now? The water gets back its taste. Due to what? Dissolution of the air again in the water. So this point we have to understand. Next one. Gases are more soluble in cold water. Cold water is at low temperature or high temperature? Cold water is at low temperature. Whenever temperature is low, the solubility will be more. Solubility will be more. Whenever temperature is less, solubility of gas in liquid will be more. That's why the gases are more soluble in cold water than in water at high temperature. Next, soda contains carbon dioxide dissolved in water. What is soda here? Did you ever drink Goli soda in the bazaar? Goli soda is nothing but what? Carbon dioxide dissolved in water. Okay. Under high pressure, we dissolve this CO2 in the water. Why we are using high pressure for carbon dioxide? Because high pressure will increase the solubility of CO2 in water. Next, when a soda bottle kept at ordinary temperature. Okay, when soda bottle is initially the soda bottle is kept at ordinary temperature, room temperature. Suppose the soda bottle is opened. That soda bottle is opened. Initially it was kept at what temperature? Ordinary temperature. That soda bottle is opened. When it is opened, the evolution of carbon dioxide. Evolution means what? The release of carbon dioxide is less compared to similar chilled soda bottle. Now, when you open the chilled soda bottle, the evolution of gas will be very high. Is that clear, ma? So what they are saying, once again, try to understand concept. When a soda bottle, which is kept at ordinary temperature, is opened, when that soda bottle is opened, the evolution of carbon dioxide is less. Okay, when you compare with what? Similar chilled soda bottle. Chilled soda bottle means cold solution will be there. The solution at very low temperature will be there. Okay, so which on opening produces more effervescence. More effervescence means what? Sudden release of gas. Sudden release of gas from solution. From solution, if a gas is suddenly released, that is called effervescence. So more effervescence will be observed when you open what? Chilled soda bottle. When you open the chilled soda bottle, suddenly more gas will come outside. But when you open the soda bottle at normal temperature, uncool, okay, in that case, less gas will be released out. Is that clear, ma? So this point keep in mind. Next, already we have discussed what methods of expressing concentration of solution. Okay, now concentration of solution is the amount of solute, solute dissolved in a known amount of solvent or solution. So already we discussed about concentration terms. The concentration of solution can be expressed in various ways as discussed below. Percentage we discussed here, W by W percentage. Weight of solute by weight of solution into 100. Okay. Next is what now? Example we discussed here. 10 grams, 10% Na2CO3 solution means what? 10 grams Na2CO3 solute is dissolved in 100 grams of solution. It is what? Weight of solution. 100 grams is what? Weight of solution means what? Weight of solvent plus weight of solute. Weight of solvent plus weight of solute together what? 100 grams here. But this is what now? 10 grams is what? Weight of only solute. Weight of only solute. 2 is for solute, 1 for solvent. Otherwise B will be used for solute, A will be used for solvent. Next, W by V percent, weight by volume percentage. In this case, we take what? Weight of solute in grams by volume of solution in ml. Weight of solute in grams by volume of solution in ml into 100. Okay, here example 10% they give, 10% weight by volume percentage. W by V percent, 10% given. Means what? 10 grams Na2CO3 solute. 10 grams Na2CO3 solute. This 10 grams is what? W2 now, weight of solute. Is dissolved in 100 ml solution. So volume of solution to be taken what? Volume of solution is equal to 100 ml. 100 cc means what? 100 ml. Next, volume to volume percentage, V by V percentage. So volume of solute in ml, milliliters by volume of solution in milliliters into 100. Volume of solution meaning what? Volume of solvent plus volume of solute. Here volume of solute means only what? V2. Only V2 is what? Volume of solute by volume of solution into 100. And so here 10% is given. W by V percent is how much is given? 10% ethanol means ethyl alcohol. Means what? 10 ml. 10 ml is what now? Ethanol. So V2 volume of solute is equal to 10 ml we have taken. Volume of solute is equal to 10 ml. Ethanol means ethyl alcohol, which is what? Solute now. Ethanol is dissolved in what? 100 ml solution we have taken. 100 ml solution means V1 plus V2 is equal to what? 100 ml. So V1 is volume of solvent, V2 is volume of solute. This total is equal to what? 100 ml volume of solution. Next, V by W percent, volume by W percent. A volume of solute in ml. So V2, solute now here 2. V means volume. So volume of solute in ml, volume of solute in solution ml, solute in ml, and weight of solution. Weight of solution means W1 plus W2. W1 plus W2 in grams. Okay, so volume in ml by weight of solution in grams. Weight of solution means what? Weight of solvent plus weight of solute in grams. So this is what now V by W percent. Yeah, V by W percent, how much is given? 10% given. That means what? 10 ml of solute, 10 ml of ethanol solute. Here 10 ml is what now? V2. V2 is what now here? 10 ml. V2 meaning what? Volume of solute in ml given here. And this 100 grams is what now? Weight of solution. That is weight of solvent plus weight of solute is equal to 100 grams. Weight of solute plus weight of solvent is equal to 100 grams here. Weight of solution is given. Okay. Next, one more is what? Parts per million, ppm. ppm stands for what? Mass of solute. That is what? Mass of solute means what we take? W2 or W1? W2 in grams. W2 in grams by total mass of solution. Solution means what? Weight of solvent plus weight of solute in grams. Okay, ma? So weight of solute plus weight of solvent together in grams. And W2 means what? Weight of only solute in grams into 10 power 6. 10 power 6 means 1 million. 10 power 6 meaning what? 1 million. So weight of solute by weight of solution into 10 power 6. And this ratio, this total ratio is called what? This fraction is called what? Mass fraction. What we say? Mass fraction. Mass fraction means what? Mass of solute by mass of solution is called mass fraction. This mass fraction value into 10 power 6. is equal to ppm. And next one, mass fraction into 10 power 9 is equal to ppb, parts per billion. So 10 power 9 is equal to what? 1 billion. 1 billion is equal to 10 power 9. 1 million is equal to 10 power 6. So here we take mass fraction, meaning what? Mass of solute by mass of solution. A W2 by W1 plus W2. Here W2 is what? Mass of solute, and mass of solution means what? W1 plus W2 in grams into 10 power 9, that is 1 billion. Will be giving what? ppb. So ppm, ppb. Next, strength of the solution. Strength of the solution is given by what? Mass of solute in grams. That means what? W2 or W1? Solute means 2. Mass of solute in grams. Okay. Divided by volume of solution liters. So volume of solution in what? Liters. So we are taking W2 in grams, and volume of solution liters. So what will be the units of this one now? Strength units will be what now? Gram per liter. Yeah, grams what now here? Weight of solute, and liter is what? Volume of solution. So gram per liter. So gram liter inverse is the unit of what? Strength of solution. Strength of the solution. So normality and all, not the syllabus. And one more important last concept is that we need to understand what mole fraction. What is that, ma? Mole fraction. See, mole fraction means what generally? Mole fraction is given by what? Mole fraction is given by x. So here, how I'm taking x2. X2 means what? Mole fraction of solute. Mole fraction of solute is equal to number of moles of solute by number of moles of solvent plus solute. Okay, the ratio of number of moles of solute to total number of moles. It is what? Number of moles of what, ma? Number of moles of solute. And what is this now? Total number of moles of what, ma? Total number of moles of solution. Total number of moles of solution. In the solution, what will be there? Solvent and solute. So both there here. So this ratio is called what now here? Mole fraction of solute. If you write now x1, mole fraction of solvent, suppose mole fraction of solvent, how to write, ma? X1 is equal to, first we write N1. N1 means number of moles of solvent by N1 plus N2. It is solution. So number of moles of solvent by total number of moles of solution. This ratio is called what now? Mole fraction of solvent. Generally for the binary solution. For a binary solution has how many components, ma? 2 components, one solute and one solvent. For a binary solution, okay. So what will be this now? X1 plus X2 must be equal to 1. 1 means what now? Unity. What is called? Unity. Unity means 1. X1 means mole fraction of solvent plus mole fraction of solute. Must be equal to what? 1. Wherever 1 is there, A is there, 1 we can take. Wherever 1 is there, A we can take. This indicates what? Solvent. Whenever we use 1, otherwise A, that will be solvent. If you use B or number 2, that will be called what? Solute. Okay. So X1 means what? Mole fraction of solvent plus X2 is what? Mole fraction of solute is equal to always what? 1. So if you calculate X2 value, if I already calculate X2 value, X1 value directly how to get? 1 minus X2. X1 value is equal to 1 minus X2. Otherwise, X2 is equal to 1 minus X1. So this is mole fraction of solute and mole fraction of solvent. The sum of mole fractions of all the components of the solution must be equal to what? 1. Must be equal to 1. So this condition we have to understand here. Is the concept clear, ma? So these are all things you have to read from material. After reading once the material, please go through the reference book also. Any one reference book you can take and read. Okay, ma? Bye. Good day. All the best.